Particularly honored to have the opportunity to speak to you today. And the honor is also great out of another reason, is namely to be able to present to you a chapter on a topic called urbanization or urban energy systems, which is an entire novelty in international assessments. Believe it or not, we had to wait for the watershed period in human history, namely for the time period that half of the world population lives in urban environments, before urban issues appeared in any major international assessment. The global ecosystems assessments or previous IPCC reports did not bother to look into urban systems, and so therefore the global energy assessment was a unique opportunity to address urban issues. I'm going to quickly run you through our main conclusions. I'm trying to do that within the time limit, so please excuse a rather rapid pace of presentation. I think in any assessment, the first thing you do is to take stock. We have mentioned the population numbers, but we have done in our assessment a much more multidimensional kind of assessment of the urbanization phenomenon, looking at land use, looking at the economy, at GDP, looking obviously at energy use, but also looking at some of our technological infrastructures like the internet. And the basic conclusion is that with the exception of land use, where urban areas are actually insignificant, accounting for between 0.2 to 2% of the habitable area of the planet, the world is already predominantly urban. Much more urban than the 50% world population living in cities suggests. According to our assessment, about between 2/3 to 3/4 of final energy use worldwide is urban energy use. About minimum 75% of the world GDP is generated and consumed in urban environments, and about 96% of internet backbones are actually located in urban areas, suggesting that also the virtual, the material infrastructure of the internet is highly place-specific and consequently vulnerable to the kind of environmental stresses urban environments impose. So the world is already dominantly urban today and will become even more dominant urban in the future. So if you take any of the UN scenarios, they produce a single one. GEA has produced 3 alternative scenarios, but the basic conclusion is the same. Expect minimum 3 billion additional people moving into urban areas or being born there over the next 40 years. So 3 billion people need housing, need transportation, and the associated energy services, need clean water, need clean air, and a livable environment over the next 40 years, in addition to all of the people that are living in urban areas and continue to be disenfranchised in terms of the urban poor, for which we have a separate subsection. I think an important message here, when we look at the urbanization phenomenon, is to look at 2 opposing environments. One is the rural environment, which is shown here on the bottom of the panel. That's the brown color. These are the people living in rural environments. I show you only one single scenario derived from the United Nations in order to simplify the exposition. The basic conclusion across all urbanization scenarios is that invariably, in all scenarios, the rural population peaks by 2020 and will decline thereafter. So that means if energy access is not resolved by 2020, 2030, well, that energy access issue will be resolved by people moving into urban environments where they have access to energy. This adds actually a lot of urgency into the energy access issue, simply from this simple demographic phenomenon in urbanization. The second important aspect is on the top part of the panel in the green, yellow, and red colors. This shows you the growth of urban population by size of the cities or size of the agglomerations. And I think this is a very interesting kind of contrast to the usual discourse when we talk about the urbanization phenomenon. Basically 90% of the literature and 90% of initiatives and policy discussions is actually focusing on the red sliver on the top, on the megacities. But in terms of urban growth, megacities are not the main drivers of urban growth. Megacities are actually relatively small in numbers. They are big by themselves, but they're small in numbers and also small in total amounts of population. The real driver and the real engine, the most important constituent of urbanization right now and also over the next 40 years into the future will be the growth of small to medium-sized cities. Now, these small and medium-sized cities pose a number of significant challenges. We have no data, we have no models, and we have no policymakers because institutional capacities are weak. A lot of room of work to really start asking questions. So for the interested PhD student here at this university who is looking for a topic, don't look at yet another study on New York or Tokyo or Beijing or Shanghai. Start to look at a small or medium-sized city of 100 to 500,000 inhabitants, and preferable in sub-Saharan Africa, because for there we have absolutely no information. The second major cluster of conclusions are that city dwellers have often lower direct energy and carbon footprints. So cities are good for the environment. They are great, not only in terms of economic exchanges and innovation, which we know from the work of our colleagues in the Santa Fe Institute, but they're also good for the environment because of a number of reasons. Structural reasons due to economic structure, density, different kinds of human activities, etc. At the same time, when we look at this conclusion, we need to add an important caveat. Our conclusion is only as robust as our system boundary and measurement models allows, and here we have important ambiguities and we have no data reporting standards, so which remains an important future tasks for assessments. I give you here an example of some of the additional work on the GEA website. When you go to the chapter 18 on urbanization, all of the support material, the working papers, and also this database. It's a database which we have developed for approximately 200 cities to assess the urban energy use bottom up, not only top down. So we look both at top down and bottom up assessments. So this panel gives you our sample of 132 cities located in Annex 1 countries. So these are the OECD countries. On the x-axis you have the cumulative population of this sample, so this is approximately 180 million people live in these 132 cities. And on the y-axis you have the resulting per capita final energy demand. So this is direct final energy use per capita in these cities. And you obviously see the dispersion, so there are some cities where per capita energy demand is exceedingly high, and then, the gradient declines. The most important information is actually in the color code. Each time a city is plotted in blue here, its resulting per capita energy use is significantly below the national average. So this city has typically between 20 to 35% lower energy demand than the national average. Each time the color code is red, that city has higher energy demand than the corresponding national average. This is largely related to differences in industrial structure. A manufacturing city which has a steel plant in it obviously will be above the national average, and a service-oriented banking city or residential city will be below the national average. The dominant color in this scheme is blue, which means that in the OECD countries, in Annex 1 countries, cities generally have much lower energy footprints and resulting carbon footprints than the national averages, which emphasizes my conclusion that cities are good for the environment. This conclusion looks actually different when we look at our sample from non-Annex 1 countries. So these are cities in developing countries. Again, the same metric, cumulative population. In this sample of 68 cities, it's close to 300 million. And we have total final energy use, which is in the same ballpark as actually many cities in the Annex 1 countries. And we have the same color code, and we see the color code is predominantly red. So in the developing countries, actually urban dwellers consume much more energy than rural dwellers, and the reason for that is primarily related to the enormous income gradient between urban and rural areas in developing countries. So that means living in an urban area means you're much richer than people in the rural areas, and as a result you have much higher energy use. This gives you a more comprehensive picture for a sample of megacities. I apologize, only megacities are available here because this requires intricate modeling studies using input-output techniques, and gives you a kind of perspective comparison between the direct energy use in the city shown as blue on this bar chart in comparison with the embodied energy, so that means the energy embodied in the goods and services imported into the city. The sobering conclusion from our assessment chapter is we have tried to make an apples-to-apple comparison of different urban energy and greenhouse gas accounting frameworks between direct and indirect and hybrid approaches. We could do it, but we could do it only for 2 cities in the entire world, London and Melbourne. That's where our information is right now. So we have enormous data and methodology deficits to really come to a comprehensive conclusion of how to account for the intricacies of resource flows in inherently open systems, which are urban systems. So therefore, a lot of room for methodology and also empirical work, which needs to be done. So very, very complicated processes, and my personal conclusion is actually for the time being actually to focus on the direct energy flows and not to try to spend too much time on international benchmarking of consumption accounts of urban energy use simply because the data are bad and we have no standardized methodology. So here, do the basic research first, agree on a standardized modeling protocol, improve the database, and then move into the international benchmarking scheme. But that's my personal conclusion. Next group of conclusions are clearly cities are special. Cities are special in as far that they have specific sustainability challenges and at the same time specific opportunities. And the biggest challenge and the biggest opportunity at the same time is density. Density up to a certain level, not infinitely high, is actually both a big challenge and a unique opportunity which can be harnessed for energy systems. The big challenge is that at high densities, even low impact or low emission systems can overwhelm the assimilative capacity of the environment or of human health. That means over the long term, over the time horizon of this assessment, urban energy systems need to be zero emission systems. Zero, not low emission systems. That's the corollary of the high population density, so zero emission systems. But at the same time, because you have this high energy use, there are enormous opportunities of energy recycling, cascading, cogeneration, intelligent systems management. And my fair guess is that the first prototypes of intelligent energy systems and more integrated energy systems, the laboratories for these experiments will be at the urban scale, because there the enormous opportunities for improvements are located. This is just to flag you the challenge which dense urban environments impose from an environmental perspective. It gives you a pollution exposure map. So concentration of ambient pollution, we use here sulfur dioxide emissions times the population. This is a three-dimensional map for China, and you see the enormous peaks or the mountains of environmental risk to human population health, which is a combination of ambient concentrations times high population density. And therefore, in these big spikes, which are the big cities, we need very aggressive environmental control measures, and over the long term, as mentioned, zero impact and zero emission systems. This is an example from my home city of Vienna, and it's an example of the kind of analysis which we have done in the chapter, is to look at the impact of systems integration. Now, this is for first simple systems integration. It's called cogeneration. It is very dominant in Vienna. And because of cogeneration, the first law efficiency of the energy system of Vienna is 50%. But this gives the impression that the system is already very highly efficient and there is no room to improve. So we did also second law calculation and exergy analysis, and in this analysis the energy system of the city of Vienna is only 17%. So you harnessed only 17% of the theoretical thermodynamically possible energy efficiency. And if you compare this to other cities, you see similar vast improvement potentials. So cities are not different from the kind of sectorial perspectives which we have seen earlier today. Cities are powerhouses for energy efficiency improvements and energy efficiency innovation. Here is where a lot of potential and low-hanging fruits are in, and many of these additional efficiency improvement effects come from systems integration. This system integration is very important. However, there's a downside. Everything which involves the name systems and integration means that from a policy perspective, it is very, very complicated. So we have here what we have called in the chapter a governance paradox, that the largest improvement potentials at the urban scale come from systemic changes and from integration, but they are also the most difficult to do from a practical political economy perspective, because they require coordination. Coordination between land use, zoning, building codes, transportation, public transport, soft mobility modes, and energy policies, all at the same time, which is, of course, a big challenge to achieve. This is my own summary. It's a stylized representation of this kind of conclusion. We did not include it in chapter because we could not agree in the writing team on this stylized hierarchy, so it is my own doing, and it tries to illustrate you this kind of paradox. On the left panel you have a ranking of measures in terms of how much they matter to determine an urban energy or greenhouse gas emission footprint. And on the right hand, you have an inverse, a triangle, that shows you the kind of leverage effect which urban policy at the local scale can have to affect this kind of patterns. So what matters most, like spatial division of labor, is this an industry city or is it a residential or service-oriented city, cannot be influenced by local decision making. Conversely, what can be influenced the most by local decision-making, like, for instance, urban renewable, locally generated renewables at the urban scale, actually matters the least from an urban energy and greenhouse gas emission footprint. Our conclusion is that for any city of a reasonable size, let's say above 1 million inhabitants, locally harvested renewables can supply a maximum of 1% of energy demand, simply because of the enormous mismatch between the high concentration of energy demand at the local scale and the dissipative and low density nature of renewable energy flows that can be harvested at the local scale. That doesn't mean that the renewables cannot be used in cities, but the renewables need to be brought into the cities, which have significant infrastructure implications which we need to consider. Being here in Stanford University, and being Stanford I can characterize as a powerhouse of energy modeling, this is an illustration of a kind of new type of generation of energy models that combine traditional engineering optimization techniques with spatially explicit and agent-based modeling activities. It was developed at Imperial College, and it gives you a kind of illustration of what you can do in order to simulate the impact of alternative policy options. And the basic conclusion is that urban form and density is as important as the efficiency of our technological devices, about 1/3 each. The energy sector itself, through cogeneration, is about 10% in comparison to that. And obviously, if you combine and integrate all of these policy options, you have the biggest efficiency improvement potentials. So at the urban scale, the big chunks to consider are urban form and density and efficiency of our buildings and infrastructures and devices which these infrastructure systems use. I run out of time, so this is a recap of my conclusions, and this is the list of my distinguished groups of authors and contributors to both the text and the GEA energy database, so for which I would like to thank you very much.